Okay, welcome everyone to this continuation of what is quantum topology, part 3, and now I'm going to start with, well, more formally what quantum topology is. If you have seen other videos on this channel, I'm not going to be very formal, so don't worry about it. But we are roughly following the outline of, quantum topology. So, chapter 1, the category thingies, with my little Rosetta Stone, doing all the work for us. So we start with categories, and essentially quantum topology will be a low-dimensional version of category theory. It's kind of comes from low-dimensional topology, but it's more like category theory in low dimensions. So I should start at the beginning and just tell you what a category is in a kind of hopefully very basic language. So here's one of my favorite pictures. We had that here as well. So people who get excited about this shape, somewhere in between set theory and category theory. So people usually say modern mathematics is like category theory, not set theory anymore. Whether that's true or not, I don't know. But people who get excited about this shape are clearly doing both. Anyway, but category theory is clearly a big part of quantum topology. So I would spend some non-trivial time just waffling about category theory. Keep in mind, I already said that category theory, we actually really want low-dimensional category theory. You'll see what that means. And I asked ChatGPT for a one-line sentence to summarize category theory, and this is what it came up with, which I actually found it's pretty good. So category theory treats functions and structures as first-class citizens. So the whole point of category theory is to look at structures, relations, functions, whatever you want to call them. It's very, very misleading if you see it for the first time, because everything will be named after what people call the objects, when in reality, everything should be about the functions and structures. And yes, in other words, category theory is a language of structure and transformation in mathematics. It's a language of transformation, right? So how things change, that's the whole point in category theory. Category theory treats functions and structures as first-class citizens. Actually pretty good, right? So that's what ChatGPT can do nowadays. So not so bad. And before I go to the formal definition, here is an example. No? So a collection, essentially a category will be a collection of things and transformations. Transformations, important. Things, you still need to have things around, I guess. And the things are usually called objects, and the transformations are often called arrows, maps, morphisms, very different names. Again, they are important, so they have many names. Huh? So here the objects are the sets themselves, and morphisms are the maps, whatever. Here the map one goes to 1, 2 goes to 3, something like that. And I really think of a category as a little blob, the universe, right? The category is just a little blob. Yeah, so this is one example. But then category theory is somehow the language of the things. Everything that fits into the framework of things and transformations. Yeah? Objects and arrows. And what we will do a lot is we have this funny category of cobordisms, which I'm going to explain in a second. Well, right now, actually. I usually call it one cop. So the category has points as objects. So here are points. Here are some more points. And the lines that connect the points as morphism. Something like that, I guess. Something like that, for example. Lines that connect the points. The last line was pretty nasty. So let me draw it again. This is also nasty. I really can't draw nicely. Anyway. And the way to compose things, let's say you have 5 on the bottom, is you just stack them towards one another. So here's another one of those pictures, just connect the lines somewhat, and you get a new picture of the same type. Very, very nice category. And now your transformations are the lines. So they're not really functions anymore. So kind of category theory takes this idea of having something object and like set and function based to the next level. Here, nothing is set and function based anymore. And that's why it's like modern, right? You kind of forget the underlying sets if you want. So this example, was one of my running examples. So as you can see, I just copy something from here. So it's one of my running examples. It's very nice. One-dimensional cobordisms. The objects are points, which are usually just denoted by bullet, and the morphisms are those pictures that you can just stack. Right, here's F is at the bottom here, and G is at the bottom here, which gives you composition in that category, while composition into somewhere here is like just composing maps. Yeah? So it's kind of a generalization of this idea of maps and their compositions. Kind of very nice. And if you really want to read the formal definition, yeah, we have some objects, yeah, we have some arrows, yeah, we have some composition. Fine, such that it's associative, identities, and whatever. No, not that exciting actually. But yeah, let's just run me through. Let me run you through it. So the way how I would define it, a collection of objects. I'm not really specific what that is. A class, a set. I don't care actually. It's not super important. And then the morphisms, the arrows, whatever you want to call them, right? So the morphisms, those guys here, such that the natural axioms. So we have the composition, yeah, f x to y, g y to z. So fg goes from x to z. There's an identity morphism. Here's my little identity morphism. And associativity, whenever that makes sense. And yeah, so that's a category. And everything that fits into that framework is a category. And I really like to think of it as just a stupid little graph. So here my objects are 1, 2, 3. My morphisms are f and g. And I also want a composition fg, which I usually read in that direction. Very strange, but this is how you read functions. If you just remember, the input of functions is always on the right for some reasons. So this is first f, then g, and this is like a category. And it's not like one is a set and f is a map. No, one is just a placeholder and f is also just a placeholder. It's kind of a very combinatorial object, a category. Yeah? It's a very combinatorial type of object. And one of the first things we learn about categories is the following. It's called coherence, and it will play an important role in the low-dimensional world. So if this is like, categories, by the way, are one-dimensional things. Why is that? Well, let's go back to that example. Yeah, it looks very one-dimensional to me. Yeah? They are lines and points, essentially. Points are the objects and lines are the arrows. And later we will see higher dimensional categories, yeah? Where you have faces and whatever. We'll see. But for now, these are lines and points, and coherence in this case just means, well, if you were looking carefully, let's just go back, I really just impose this type of relation, right? So associativity for three morphisms, and just one bracket change. But you could just say associativity is you don't need any brackets at all, which is actually the correct definition of associativity. And turns out that these two are the same. So just imposing this one, which is one relation, compared to imposing infinitely many relations, the other one. So they're the same. And the proof is pretty nice. So I think of this bracketing as like this little tree here, right, where f and g were bracketed first and then h comes. So this little trivalent tree. So general associativity would be any way of doing this bracketing thing, so all the kind of swaps on this tree, they're the same. It's kind of fun. And it's not quite clear to see why this should be the case, right? This is a much weaker condition. It actually looks much weaker. And B is a much stronger condition. You apply for every bracketing is the same compared to this specific bracketing is the same, right? But it's kind of a fun thing to do that. And the way how I would do it, I'll leave it as an exercise, is the following. So here's our little picture. And all you need to do is, I can zoom in a little bit. Let's see. Here's this corresponding type of picture. So here are 1, 2, 3, 4 symbols, right? Here are just 3 symbols, kind of the next step. And I am only allowed to do that type of swap, right? So I'm only allowed to do like this type of swap around one vertex here. Yeah, from here to here, for example. Or I'm allowed to move that one from here to here or whatever. And I want all of them to be the same. And the nicest way to prove that is that the kind of diagram you draw where you put an edge between them, if there is an operation of this type, just one of the tiny operations, yeah, you just put an edge between them, there's one tiny operation, and you want that this thing is connected. And that's actually not so difficult to prove. And this thing has a name, the shape you see, the red shape. It's called the associahedron for the obvious reason. Yeah? And then you're done, because clearly B implies A. Yeah? B is saying everything, every bracketing can be changed, and A is saying a specific bracketing can be changed. Filling in the details is a fun exercise. Anyway, so this was the first more formal video, I guess. This is as formal as it gets, by the way. So I hope you enjoyed this video, and I also hope to see you next time.